Welcome everyone. Today we're going to continue our path talking about our functions of multiple variables. We dealt with our partial derivatives previously, looking at the derivative in purely the x direction or the y direction. Okay, so now, because right now that we're dealing with 3D coordinate systems, more often than not, we're not going to travel purely in just the x or y direction. Think of your life, right? We can go in any direction. So now we're going to talk about our directional derivatives and of course a tie into the gradient vector. So let me start to share my screen, my docam, and we'll get going. All right. So here we are, directional derivatives and the gradient vector. Okay. Starting off, like we had previously mentioned, right? Previously, we had our partial derivatives. Right? If we had our function, we'll just deal with a function of two variables for now, right? That z is equal to f of xy. Then we could take our partial with respect to x, right? That kind of curly D notation, since that function has two independent variables. We want to identify the variable that we're taking the derivative with respect to. So we can take that derivative, that partial derivative of our function with respect to x, right? This is going to look at that limit as h goes to 0, considering what happens when we let that x variable change slightly, x plus h minus f of x all over h, right? Very similar to our 20a, our Calc 1 limit definition of the derivative. And then we take that derivative, seeing how we're changed. Okay, if I leave the y constant, how is that function, how is that surface changing in that x direction? And we get our partial of f with respect to x, or that f sub x, that little subscript notation. And similar discussion for y, that partial derivative with respect to y, going through dot 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 df dy or f sub y, right? So now with these two partial derivatives, we're looking how it's that function, that surface is changing purely in that x direction, okay? That rate of change, that derivative, slope, if you will, in that x direction, holding y constant, okay? And then here, our rate of change in the y direction as though the x is constant, okay? Let's see right there, the direction of y, x is constant. But then comes the big question, right? But really, we can travel in any direction on our surface and consider the derivative, right? That slope, that rate of change in the specified direction. Okay, so instead of being locked into just looking in the x direction, the y direction, what if instead I can face any way, right? Again, going back to thinking with our mountain climbing, right? Those topology maps where we're looking at the landscape, right? Where those hills and valleys are, right? If we're standing on that hill, and so, okay, if I face this direction, if I face east, if I face west, northwest, whatever it might be, right? If I face that direction, what would be the slope, right? How quickly would I be descending? How quickly would I be ascending in that landscape along that surface, right? Going down that hill, thinking about skiing, right? All these different various outdoor activities, right? How would that aspect, how would that rate of change, that slope feel? Okay, and so then drawing this, if I can, right? So again, if I have some surface, and I think out of kind of ease, we can imagine having this kind of like paraboloid. We can have that surface where, depending if we were going in that x direction, okay, if I held y constant, right, we can imagine this kind of feel where at any location along, we can think of this like kind of like our f sub x, right? Or likewise, if I go in the y direction, holding x constant, we can get at that same point, right? Maybe an f sub y. So if I was facing purely in that x direction, going along that y direction, we can identify those slopes. But now, what if, again, at that point or whatnot, what if I go in some random direction? I'm not along the x or y axis, not I or j vector directions, right? What would that slope, what would that derivative, what would that look like? Right? If this is my direction, what would that derivative look like? Okay, so that's that discussion. And so, pardon me, in that work, we get into exactly that directional derivative. Okay, so now to find this directional derivative, okay, right? That is the derivative of our function. We'll start off with 2 variables, but we can expand it to a function of 3 variables, 4 variables even, okay? In the direction of a unit vector, we're gonna call it u hat. Remember the little hat notation makes it a unit vector. That magnitude 1, okay? And again, the reason why we need this unit vector, because we're only worried about that direction, okay? When we start to work on it, regardless of whether that vector, that direction, okay, that vector v we had before, might be some really long vector, a really short vector, all we're really concerned about is facing what direction. So that's why we can normalize, if you will, right? We can reduce that down to a unit vector. Take some vector, divide by its magnitude, right? That way we can really focus on direction and not magnitude of that vector b that we're facing, okay? And so with that said, we can start to incorporate that, right? So now it's kind of identifying, okay, if I'm not going purely in that x direction, not going purely in the y direction, then what derivative, what slope, right, are we experiencing in this direction of the unit vector u, okay? And again, it kind of really ties back into what we had done back in chapter 12, thinking about those components, right? Those dot product work we had done, the scalar projection of vectors on another, okay? So taking those components from our partial of x, partial y, what change was feeling in the x direction, what change is feeling in the y direction, and putting those together, then, right, some going, I'm going to get a little bit of change in x, a little bit of change in y, depending on which way I'm facing, and putting those together to identify that kind of final derivative that's experienced in a particular direction, right? So I know that's kind of wordy there, all right? So let's see, okay? So for our directional derivative, we'll see that computationally. F at some point, x naught, y naught, okay? In the direction of a unit vector, get this language from the textbook, u, components a, b. Notation wise, this capital D sub u, right? This is our differential operator, that derivative. In some Calc 1 courses, we look at different notations, and that differential operator is a notation. It's using differential equations, Math 32 here at MPC. So that derivative in the direction, right? So again, those projections, those component notations we talked about before, little subscript. So it's in the direction of the derivative in the direction of u of that function f, okay? In particular, at this point, x naught, y naught, that's going to be equal to, and then as a limit, now we're going to let both x and y change, because now instead of just going purely in the x direction or y direction, we're going in some general direction, v, or as it is normalized, the unit vector u hat. So I'm going to take x naught plus h times it, right? So some portion in that x direction, a component, y naught plus h times b. So some component in the y, the j direction, h times b, minus f of x naught, y naught, all over h, right? So very similar to what we had done with those partials, but now actually allowing both x and y to change, okay? And so that's how we're defining that directional derivative, but kind of like what we did with our partials before, right? Now really all we're doing is seeing this component that h is being multiplied by a, h is being multiplied by b, those components of this unit vector b. And if I forget about it, if I let that b be 0, for instance, if this is really just a vector in the x direction, 1, 0, then this becomes just like our partial with respect to x, right? If this is a unit vector solely in the y direction, the j direction, 0, 1, for instance, then that becomes that partial with respect to y. And so if we start to kind of put those components in, okay, I'll put a little dot, 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 thinking about separating that limit, right, as well, using some of our old 20A and even 20C, Calc 1, Calc 3 limit laws. we can start to separate this and start to see, well, this is going to look like the partial with respect to x evaluated at that x naught, y naught times a, right? That component in the x direction of our unit vector plus f sub y at x naught, y naught, that partial of that function f with respect to y evaluated at that point, x naught, y naught, times b, right? So again, kind of putting the x components directions together, that partial, okay, how much in that x direction is that derivative being felt, and what component of that x direction are we going for our unit vector u? Then how much of that y derivative are we getting in that b, right? That y direction of b. Putting those together, taking that combination, we get the overall directional derivative, the derivative in the direction of u of that function f at that point x naught, y naught. Okay. So here, this is the derivative of that function f in the direction of u at the point x naught, y naught, right, from our domain. Okay. So when we start to see on our surface, we're looking at this point, x naught, y naught, from our domain. We can send that through our function, get that z coordinate, right? So say on that location on our surface. Then when I look in the direction of u, okay, once I'm standing on top of that hill, standing at that point and face my direction, what is the derivative? What is that slope, right? Positive, right? Okay, we're starting to climb. Negative, we're starting to drop. That increasing, decreasing. What are we experiencing at that point, at that location? If I face that particular direction, that quantity. Okay, and again, that u is always a unit vector. Okay, so let's look at an example. Then we can get into some notation, some discussion with that gradient vector. Okay, so for example, though, let's check out here. Book real quick. Here we go. So let's say we're given this function. Let's go g. I'm going to change my variable slightly just to match up to what we had talked about, x and y. Other times you might see the parameters s and t, u and v, right? Those independent variables. But let's say we're here, and this is x squared e to the negative y. Okay. So let's find the directional derivative of the function at the point 3, 0 in the direction b is equal to 3, 4. Okay, or 3i plus 4j. And again, if we want to, we can put that function into a graphing tool to see what that surface looks like, and then identify in that xy plane that 3, 4, right? X is 3, y is 4, kind of pointing in that direction along that surface, right? To kind of stand underneath the shadow of that surface, right? And we point in that direction. What slope would we be experiencing on that surface? Okay, above this point in particular, x is 3, y is 0. in that xy plane, okay? And again, I want to draw the picture for now, but again, going to a graphing utility, we can certainly do so. But let's look at the calculation, right? So from our information, right, overall, you have now our function g of x naught, y naught. So the directional derivative, so the derivative of this function g in the direction of u at this point, x naught, y naught, that's going to be our partial of g with respect to x, evaluated at x naught, y naught, times a plus g sub y, the partial of g with respect to y, at x naught, y naught, multiplied by b. Right, that's what we're going to be plugging into at the end. But now we need our components, right? So in this work here, this is a unit vector, right? U hat is v over the magnitude of v. I'm doing those double bars just to be extra clear here. So in this case, if v is 3, 4, the magnitude of v, the square root 3 squared plus 4 squared, right? The sum of those squares. 9 plus 16, 25, right? That 5, a common vector. So in this case, u hat is going to be 3, 4 over 5, or our unit direction vector, 3/5 and 4/5, both positive from the original vector. Now, for our partials, if our function is that product, x squared e to the negative y, my partial with respect to x, taking with respect to x, this is a product, this e to the negative y, since there's no dependence on x, is just a constant, it's going to stick around. The derivative of x squared, 2x, or 2x e to the negative y. G sub y similar. Now that x squared's a constant, derivative of e to the negative y, e to the negative y times the derivative of negative y with respect to y, negative 1. So we're going to get negative x squared e to the negative y. That's our general partial derivative, right, expression. But now we have a particular point. So at that point, 3, 0, what are we going to get? 2 times 3 e to the negative 0, right? E to the 0 is 1. There's no negative 0, which is 0. 1 times 2 times 3 is 6 there. G sub y at 3, 0. Negative 3 squared times e to the negative 0. 1 again. 3 squared is 9, negative 9. So there's my g sub x, g sub y components. Okay. So finishing this up then, my directional derivative d in the direction of u of our function g at that point, 3, 0, that's going to be equal to g sub x at x naught, y naught, 6 times a, the x, so the I component of our unit vector, 3/5, plus g sub y at our point, negative 9, times the y component, the j component of our unit vector, 4/5, sum of those. And what are we getting there? 18/5 plus a negative 36/5. Check my arithmetic. And the end, negative 18/5, right? So in this case, at that point on our surface, when x is 3, y is 0, we can plug into our function, get our z coordinate, right? 9 times 1, 9, positive 9. Standing on our surface there, facing that direction of 3, 4, or the unit direction, 3/5, 4/5, right? Still facing the same direction, just a shorter vector to consider. But that experience then, negative 18/5, right? We're going downwards. So negative 3 point, what's that going to be? 3 with a remainder of 3, so 3.6 downwards. Okay, think about that slope going down in that direction. Right? And this is like our slope in that direction of u on our surface. Okay. That's our slope in the direction of u on our surface looking down. Okay. All right. With that said, that calculation then. So going back into that notation of f, sorry, right? If I leave off my point for a moment, f sub x times a plus f sub y times b. If we look at these components, kind of like we've done, the fact that we're multiplying and adding, that calculation is like a dot product. So if we consider those partials, f sub x, f sub y, the partial respect to x, partial respect to y, as a vector, we could dot it with a unit direction vector AB. That would be equivalent. And this vector shows up in a lot of different calculations, tools that we use. So we give it a name. This is our gradient vector. Okay. So our gradient vector, text-wise, the grad, that function f, or here, the symbol that we're going to see over and over, the one that we want to kind of get used to dealing with. Okay. This kind of inverted delta, upside down triangle of f. And they said this is read as del f. Okay. But the gradient of f, del f, right, that symbol, but that's exactly equal to, right, our partial of f with respect to x, partial of f with respect to y, right, or our notation, our subscript notation, f sub y, f sub, or f of x, f sub y. And that can be expanded to more dimension as well. If we have a function of 3 variables, function of f as x, y, and z, then we said include another component, df, dz, partial of f with respect to z, so on. Okay. And so then our directional derivative, we can see it as our gradient vector of f dotted, okay, I can make it green, dotted with that unit vector u. Okay. And so that gradient vector is going to be used in a lot of our different calculations and tools as we go along. Okay. And so a important and interesting property of that gradient vector okay, we look at that at some points, and we get that gradient, and again, we evaluate at a particular point. So in that subscript f of x, f of y, we plug in a particular point. This gradient vector points in the direction singular, sorry, of maximum, right, the biggest possible increase for that function f at the point x naught, y naught, right? So when we evaluate and we get, right, since that's a vector with that gradient, we plug in a value for x and y to compute. He's going to give us some vector, and that's going to give you the direction to face. Okay, if I'm at that point, x naught, y naught in my domain, I go to my surface. That gradient vector is going to point me in the direction of maximum increase, right? So if I'm trying to get up that hill as fast as possible, I find that gradient at that point, and that's going to point me in that direction, right? Or likewise, if that's going to be the maximum, when I go the opposite direction, right, when I switch my signs, so that's going to be my maximum, the gradient. If I flip around, that's going to be my steepest decrease. It's going to do the opposite, right, if I go the opposite direction. So when we start to work on these steps, right, thinking again about using those tools in mapping and working with those, right? Thinking about if we're planning a city, right? Thinking about that water flow, and we're trying to grade, we're trying to kind of level off these different sections of a hill that we're building the town, building on. And you want to say, okay, if I point this direction, that's going to be the most rapid decrease, or again, vice versa, increase. So we can start to plan those directions, those aspects in engineering, in building, whatever it is we're doing. Okay. All right, I'll leave it at that to get us started with that directional derivative and practice calculating. Okay. Very good.